Hi there! In this session we're going to learn how to use MATLAB to solve delayed differential equations. Delayed differential equations, or simply DDEs, are a class of differential equations that the delayed versions of the states and functions are involved in the equation. For example, let's have this equation as y dot, the derivative of y with respect to time, for example, minus 2y plus y, but evaluated in a time 1 unit before the current time, y at t minus 1, plus 1 equals to 0, for example. This is a delayed differential equation. If we would like to be exact, we can add t here as time index, as well as here, and this is the delayed version of y. And for example, if this is y at the time t, this would be, for example, y t minus 1, and the derivative of y here is dependent to the current value of y and the value of y at t minus 1 plus a constant term. This is the simplest form of the delayed differential equation. Generally, this time delay can be a function of time, a constant, and can be function of state and function as well. And generally, the delayed version of y dot is also can be used inside delayed differential equations. So we have 3 solvers in MATLAB, and we can use them to deal with various kinds of delayed differential equations. The simplest one is the DDE 3, which is capable of dealing with constant delays. And the other one is the DDE SD, which can deal with state dependent delays. And the final and third one is the DDE NSD, which can deal with state-dependent and neutral type delays, which means both y and y dot have delayed versions in the model. And we're going to learn how to use these functions, and they are very similar to each other. And we'll start a very simple example to solve, for example, this problem. They're very similar to each other, and firstly we'll start with this simple example. Let's copy the equation and have this a new slide. Okay, here this is the model we have. The only delay which is defined here is 1. This is the single delay we have. And also we need to specify a history of this model for times before 0, before the beginning of time. We must specify some history. And here, for example, assume that yt for these values equals to 1 for all of them, for all times before the 0th second. We have the yt equal to 1, and that's the history. Now we're going to use DDE 3, this function, to solve this problem. Okay, let's implement a model here within a new M file. Firstly, let's define this model. The general form of this function will be as this function, which returns the difference of y, differential of y, the derivative of y, and let's define this as DDE func. It's okay, you can name it as you wish. And DDE func, which accepts t, the independent variable, y, the value of dependent variable, and some lagged versions of this. We can name it as L, Z, whatever you want. And these are the lagged versions. You can say it as YL too. the lagged versions, the delayed versions of y at the second. And now, because we have just a single lag here, the YL would contain just a single element. And because y is scalar, this would be a scalar too. Okay, the y prime, or we can say y prime is, okay, let's use the y prime. Y prime equals 2. Y prime equals 2. Let's move this to the other side and rewrite this. We can write y prime at the time t equals to 2yt minus yt minus 1 minus 1. And this is the equation we have. And yp equals to 2 times y minus yl and minus 1. That's it. We defined the DDE function here. Okay. If you are using older versions of MATLAB, you cannot use the function inside a script, and you must either define this script as a function or define these functions in other files. Remember this. But I think for versions higher than 2017, we are able to define functions inside scripts. Okay, this is the function of DDE func. Now, let's see the documentation of DDE 2.3. This receives DDE func, lags, and we can specify it, and some history. We can specify the constant value for this, and we must specify tspan. Okay, let's call the function and have the solution of this function. Let's copy this and paste it here. This is the DDE func, the model, and where are the lags? We must define them. Lags are just 1. We have a single lag, which is 1. Okay, the history. We can specify it as a function. Generally, we can specify it as a constant. Okay, we can specify this as y hist of t, and always we know that this is equal to 1 because we defined here as this, and that's the history. So we can pass to it y hist, and tspan is from 0 to tf, or we can use the t itself and we can define tf as, for example, 5, and t as linear space from 0 to final time. 100 timestamps will be enough, I think. And we must add some @ here to create a function handle. And that's it. If we save the program and run it, we'll have the result here, and the solution contains x, which is t actually, and y, the output of this. And okay, let's plot. We can say y equal to sol.y and t equal to sol.x. Let's plot y versus t and have the result, and this is 1. Okay, you see from 0 to 5. I think you see by providing a t which contains 100 timestamps, we don't see the same timestamps here, and we just need to pass 0 to final time. And now we can specify this t, and using the function deval, differential evolution evaluation, and pass it the solution and the t here, and this will return the y at these timestamps. And if we run this, we'll get this result, and we have the solution in 100 timestamps. Okay, let's change the history function here. For example, we can use the cosine of t. Okay, if we run this, we'll receive this result. Or, for example, we can do this minus t, and you can get this result, and this is the result of the model. Here we have the indicator in yellow, and because the t does not appear in the model explicitly, we can ignore it by tilde notation. And if we change the model, for example, if we change this constant, we'll have some other solutions if we'd like. And let's turn back the... Okay, let's go back to the original model and let's try a more complex example, and let's write down the equations of the DDE and solve the model. Okay, we have a system of delayed differential equations here, and the first one is given by y1 dot equals to y1 t minus 1, and the derivative of second state variable is y1 t minus y1 t minus 1 plus y2 t minus 0.5. Half of time unit, we have the delay, and the third one is this, y2 t minus y3 of t. And the history for all of t's less than or equal to 0, we have these values, y1 t equals to 1, y2 t equals to 0, and y3 t equals to minus 1. And let's solve this problem. Let's go to MATLAB, copy this code, and define the DDE func here. Remember, we have two lags here, and we have 1 and half as lags. Why? Because we have one lag here, they are same, and another lag here, another delay term here, which is half. And all other time indices are in the current time. So we have a lag of 1, lag of half, and that's it. And we have y here. This contains 3 rows because of 3 state variables and 2 columns. And we can define first lag as YL, the first column, and YL2 as YL, the second column. And remember, this corresponds to lag equal to 1, and this corresponds to lag equal to half. And now the model. YP is given by this. The lagged version, the first lag version of Y1, so YL1, the first component. This is the first lagged version, and this is the first component. And we have Y1 minus exactly the same term as above, YL1, 1, minus plus YL2 and the second component of that, because we have the second component of the second lagged version. And finally, we have y2 minus y3, and we can now define the y hist here. Y is equal to 1, 0, and minus 1. Or you can simply define this as this function, and this is also not needed. You can replace it with tilde if you want. And let's save this as app2. Now we have lags, we have DDE func, we have history, and this is delayed differential equation, and let's solve it. And this is the solution of the model. This is the solution of the delayed differential equation. If you want, you can change the number of timestamps here. For example, for 200, you will get a solution with more data points. Or, for example, you can reduce this to 20 points if you want. And you see we have the solution here, and we can also have a phase plot of this. And let's add some subplot here. And let's see what is this has 3 rows, and so we plot y, the first row, versus the second row, versus the third row, and we have the phase plot here, and we can turn on the grid to have a better perspective of the three-dimensional figure, and that's it. This is the trajectory of the system in the state space, in the three-dimensional state space of the model. Okay, that's it. We used the DDE 2.3 to solve two problems of fixed and constant time lags. Okay, now let's define another model which has analytic solution, and we can check for the correctness of the solution. We have y1 dot equal to y2 and y2 dot equal to minus y2 of some time tau times y2 t squared times e to the power of 1 minus y2 t. And what's the tau? Tau is a time delay, and it is related to the value of state as this, e to the power of 1 minus y2 t. And this is a sample of state-dependent delay. And we know that this model has an analytic and exact solution in this form, which is y1 equal to natural logarithm of time, t, and of course, according to this equation, we have y2 equal to inverse of time, and we'll use this as history for solving this delayed differential equation. To solve this problem, we will use DDESD, and SD means state dependent. Okay, we must define some functions, but firstly let's see the documentation for DDESD. DDESD accepts the function. Okay, delays also are functions of time and state, and also history and t-span. It is very similar to the DDE 2.3, but this time delays are functions. And let's copy this and let's define the delays here as a function. Function delays or lags are defined by, we can define this as D, delays of time and state. And we know that we have a single delay which equals to e to the power of 1 minus second element of y, according to this relation. Okay, so we have this time as delays. Okay, we can replace this with tilde. We are going to use DDESD. We pass DDE func to it. We pass function handle of delays here and yHist, and that's it. We'll remove these lags as well. And now we must define the DDE func here. We have YL as the lagged version of y, and because we have a single delay here, YL will have single entry in that. And let's define y prime, and the first one, y prime, is the second element of state. Okay, and the second one is the minus the second element of lagged version. Okay, the second element of lagged version minus, and times squared the second element squared. Okay, y2 squared times, we can add some spaces for readability if you want, and e to the power of 1 minus y2, e to the power of 1 minus y2, and that's it. We define the model here, and the history will be as this. We have ln of t here, and you know that we represent natural logarithm in MATLAB and various programming languages using log, and 1 divided by t, and we have the yHist here, and that's it. We defined all of functions needed to call the DDESD, and let's save this and let's call, and we have an error here. Sorry, this should be plot, and we have two state variables here. And okay, let's see why we don't have any solutions here. I think we have some mistakes in the implementation of model. Okay, let's run the program, and we see that it's empty. And if we check for y, we'll see that we have infinity here and nans after that, because we have the logarithm not defined in t equal to 0. So we define t0 here as 0.1, and we define t0 here and t0 here for skipping the 0 and infinity logarithm and inverse values of the history. So let's run the program, and we have the result here, and these are the states, and this is the state trajectory of the model. Let's increase the number of timestamps here and rerun the program to have a smooth result here. You can extend this timestamp, get a wider view of the results, and that's it. We have the solution of a system with state-dependent delays given by this model. Okay, as another example of the neutral type delayed differential equation, we have the final example of this session as y dot at this time equals to 1 plus yt minus 2y t divided by 2 squared and minus y dot t minus pi. And you see we have a delayed version of y itself and delayed version of y dot, and it is a neutral type DDE, and this equation has an analytic solution, exact solution of this form, that is yt equals to cosine of t, and we'll use this as our history in this example. And let's run the program. We can copy this, and let's define delays, DDE functions, yHist, and etc. And let's see the documentation for DDE NSD, the function we're going to use to neutral type DDEs. This accepts the DDE function, delays of y prime and history and t-span. So we must define another function for delays of y prime. Okay, and other things are almost the same and equivalent to each other. Okay, let's define the delays of y. We can replace this y delays and rename all of its usages in the script. The first delay is, according to this, t divided by 2. Okay, t divided by 2, and we must replace this with this. And we have yp delays too. We can make the definitions much more compact. Yp delays, and we have t minus pi here, and the DDE function y prime is given by this. We have the y lagged version and yp lagged versions here. Because of the neutral delays, we have the delays of y prime here, and we have this 1 plus y minus 2yl squared plus minus ypl. Okay, that's it. This is this term y at this time, t divided by 2, and this is the y prime at this time, because we defined delays as this. And now the history is cosine of t, and you can save the program and call the DDE NSD. We provide DDE function, and then according to this documentation, delay of yp and history and t-span. So we have y delays here, and we have yp delays here and y-hist and start from the 0th second and up to 10, and let's call the program. Now this is not needed and we have just one state variable in this model, and let's run. We have this, and you can extend the timestamp here and have the results. And I think we have an error in the definition of our model. Let's change this final time to pi, and okay, this is the result we expect to get. And if we have the y exact here as a function of t defined by y-hist of t, we can plot the y exact here, and let's show the legends: numerical solution and exact solution, and we can plot it, and you see that they are same, and we can compute even the value of error. Subplot 1 to 1, and let's define e as y exact minus y, and we can plot the value of error here, and let's run. Oh, sorry, this should be 2, and this is the error. You see the magnitude of error is of order 12 times by 10 to the power of minus 4. It's about 1,000th. And that's it. We have a pretty accurate solution of this DDE, which has time-dependent delays and delays of derivative of the function as well. And that's it. We used all of these functions, DDE 23, ST, and ST, to deal with various types of delayed differential equations, and we're done. Hope that this video tutorials was helpful for you.